In this lecture, we'll be studying properties of positive definite matrices. Specifically, we'll look at some classic theorems for such matrices. First, let's recall the definition of a matrix being positive definite. So a square matrix A in Rn by n is positive definite if x transpose Ax is positive for all vectors x in Rn such that x is non-zero. So recall that this is a quadratic form. Any vector x we consider a column vector. So this is a 1 by n times an n by n times an n by 1. And so the result of this product is a 1 by 1 or a scalar. So A is positive definite if this scalar, this quadratic form, is always positive for any non-zero vector x. Slightly weaker, we have that the matrix A in Rn by n is positive semi-definite if x transpose Ax is greater than or equal to 0 for all x in Rn. So slightly weaker because we can allow this quadratic form to be equal to 0. And finally, we recall the definition that a matrix A is symmetric if A equals its own transpose. And that means that it is a reflection about the main diagonal. So if you have your main diagonal here, then everything that you have below the main diagonal is a reflection of everything above the main diagonal. Our first theorem is also something we looked at in our first lecture on this topic. If we suppose that A is a symmetric positive semi-definite matrix, then we have the following result. We have the absolute value of any entry is smaller than the average of the diagonal entries to which it corresponds. So if you choose an off-diagonal entry, you can go to the corresponding diagonal entries and take the average of those, and you will get something larger than the absolute value of that off-diagonal entry. We also have the result that the absolute value of any entry is less than or equal to the square root of the product of the two corresponding diagonal entries. And we have that the maximum over all I and j, the maximum absolute value of all the matrix entries occurs on the diagonal. So the biggest value appears on the diagonal, which is positive. And finally, if you have a zero entry on the diagonal, then both row I and column I of A consist of all zeros. And in that case, the matrix is not positive definite. That is a type of degenerate case where you have a matrix is positive semi-definite, but not positive definite. So in that case, you have a 0 showing up on that main diagonal. And because of that, that forces zeros for the entire column and the entire row associated with that 0 diagonal entry. And of course, here you can actually see that the matrix A cannot be invertible because you can't have a column of zeros or a row of zeros and have a matrix be invertible. So these are some basic properties of a symmetric positive semi-definite matrix, and the idea is that you have a weighty diagonal. So the maximum entry occurs on the diagonal, and then these off-diagonal entries are in size smaller than the average of their corresponding diagonal entries. And so if you think of the entries of A representing, if their absolute values represent mass, you can think of most of the mass, or a lot of the mass, is concentrated on the diagonal. let's think about some more theorems. So first, suppose that A, matrix R n by n, is symmetric and non-singular. Then its inverse is also symmetric and non-singular. Of course, non-singular we get for free because we know the inverse of A inverse is A. But it's true that if A is symmetric, if A is symmetric and non-singular, remember non-singular we should mention is synonymous with invertible. So if A is symmetric and non-singular, its inverse is also symmetric and non-singular. We also have this result that if you have a matrix A that is positive definite, then A is also non-singular or invertible. And the idea there is that a matrix being positive definite is a stronger condition than that of invertibility. A positive definite matrix is an invertible matrix. But it does not go the other way. An invertible matrix is not necessarily positive definite. One of the nicest properties of symmetric positive semi-definite matrices is that of the Cholesky factorization. So suppose we have A, symmetric positive semi-definite. Then there exists a lower triangular matrix L in Rn by n such that A is equal to L times L transpose. L is called the Cholesky factor of A. Lower triangular means you have entries on the diagonal and below the diagonal, but everything above the main diagonal is 0. And so this is a very convenient way to factor a matrix. You often think of it as the square root of a matrix. This is a lot like writing A equals, you have its square of its root on the right here. This comes in incredibly handy in computations, proofs, and derivations. In fact, some of the theorems in this lecture can be proved by calling upon the Cholesky factorization. And this works in the positive definite case and the positive semi-definite case. In the case where A is positive semi-definite but not positive definite, you'll get at least one 0 appearing on the diagonal. But this is a very handy factorization. And often, really, when you think about nice properties for a matrix, symmetric positive definite is one of the nicest. And this really is one of the reasons for that. A couple more theorems. If A is symmetric positive definite, then so is its inverse. If X, square matrix, Rn by n, is non-singular, then A is symmetric positive definite if and only if X transpose times AX is also symmetric positive definite. This one is fairly quick to prove. Hint, hint, Cholesky factorization helps you substantially here. We have a couple other characterizations of symmetric positive definite matrices. The first deals with the kth principal minor. If A is a square real matrix, we define delta K to be the determinant of the upper left-hand corner of the K by K submatrix of A for K going from 1 up to n. Delta K is called the kth principal minor of A. The easiest way to understand this is to look at it visually. So the first principal minor, when K is equal to 1, is the upper left 1 by 1 submatrix. And so that would be just this A1, 1. To get the second principal minor, we do the 2 by 2 submatrix in the upper left-hand corner, and that gives us this submatrix here, A11, A12, A21, A22. For the third principal minor, we have the 3 by 3 in the upper left-hand corner, and that gives us this. And notice that these are determinants. So remember how we calculate a determinant. Here, for a determinant of a 1 by 1 is just a number itself. For a 2 by 2, we go top left times bottom right. So this would be A11 times A22 minus top right times bottom left, A12 times A21. For a 3 by 3, this breaks down into the sum of 3 2 by 2 determinants. And the 2 by 2s are computed this way. So this is how we define the kth principal minors of a matrix. And we have this result that if we have a square symmetric matrix and delta k is the kth principal minor, then that matrix A is positive definite if and only if all of those principal minors are positive. So the first, the second, the third, up until the nth must all be positive. We also have the result that A is negative definite if and only if, in this case, they alternate in sign. So we would need the first principal minor to be negative, because we would have a -1 to the 1 here. The key is they alternate in sign to have negative definite. Now you may say, what does negative definite mean? We define it here. And it's not really a surprise. It's the same definition as positive definite, except we reverse the sign. So our square matrix is negative definite if that quadratic form associated with the matrix is always negative for all non-zero vectors x. And we say it's negative semi-definite if that less than 0 becomes less than or equal to 0. Further, now that we have positive definite, positive semi-definite, negative definite, and negative semi-definite defined, a matrix A is indefinite if it's neither positive semi-definite nor negative semi-definite. So here, in this kth principal minor characterization, we see that the result for positive definiteness is nicer than the result for negative definiteness. But it is what it is. Positive definite is equivalent to all positive kth principal minors. Negative definite is equivalent to alternating kth principal minors. That leaves us with one final theorem to look at in terms of how we can characterize symmetric positive definite matrices, and that depends on the eigenvalues of the matrix. Let's recall the definition of an eigenvalue. If we have a matrix A, Rn by n, the scalar value lambda is an eigenvalue of A if there exists a non-zero vector v in Rn such that A times x is the same thing as lambda times x. So multiplying x on the left by the matrix A is the same thing as scaling the matrix by the scalar value lambda, the eigenvalue. Eigen comes from German for characteristic. So we call this a characteristic value of A. And these are very important values for a matrix A. And one of the ways we see this is in the next very elegant theorem to help characterize symmetric positive definite matrices. So suppose we have A in Rn by n, symmetric. Then A is positive definite if and only if all of its eigenvalues are positive. A is positive semi-definite if and only if all of the eigenvalues of A are non-negative. And then A is indefinite, if and only if A has at least one positive eigenvalue and at least one negative eigenvalue. So this is a really nice way to characterize a symmetric matrix being positive definite. And this is a quick check. So when you're working in different applications with matrices, if you want to check whether or not a symmetric matrix is positive definite or positive semi-definite, get its eigenvalues. It gives you a nice, quick way to check this. Now, in summary, these are all important theorems dealing with positive definite, specifically symmetric positive definite matrices. It's good to be familiar with them. It's good to know how to use them. It's good to know how to prove some of these things. There will be another lecture where we prove a couple of these just to illustrate some of the techniques and how it's done. But when you deal with positive definite matrices, these are handy things to think about. In particular, the eigenvalue characterization. The kth principal minor characterization is nice, but it's not as helpful as the eigenvalue characterization typically. And the Cholesky factorization. I would say the eigenvalue result and the Cholesky result are two that you can find yourself using in many different settings. All of these results together should give us a feel for the symmetric positive definite matrix. And again, these come up a lot in many different settings. And because of these properties, they're quite nice to deal with, especially when compared to other matrices that do not have these types of properties.